Hello and welcome to discussion 4 for CS 61B. Today we're going to be talking about inheritance. So first things first, let's get some announcements out of the way. Project 1A is due Monday, which has already passed if you're watching this video. Project 1B is due this Friday. And don't be afraid to use slip days. We gave you guys 15 slip days for a reason, so please don't worry if you have to use 1 or 2 for this project. Lab 4 has a mandatory checkoff, but it involves a solution for Project 1A, so please only go after you've turned in the project. And yes, we will know if you go before you finish Project 1A. And lastly, please do the weekly survey as always. So let's get into some content review. So we've already talked about classes in discussion a couple times in the past, and so now we're going to talk about how classes relate to each other. So firstly, subclasses are classes that extend another class. So in this case, Pitbull and Corgi are subclasses of dog. This means that the Corgi class has access to everything a dog can do, in addition to anything specific that is just a Corgi action or a Corgi attribute. On the other side of this, superclasses or parent classes are classes that are extended by another class. So in this instance, dog is a superclass. A class can be both a subclass and a superclass. This is more of a relationship, kind of like saying dog is like the mom and Corgi is the child. So it is possible, for instance, dog to extend different class. It's possible for Corgi to be a superclass. This is just a relationship between two classes. Classes can only extend one class, but they can be extended by many classes. And this kind of makes sense, right? Because if you're extending a class, you're saying I am a more specific version of this class. So it doesn't really make sense to say I'm a more specific version of these two separate classes. Moving on to abstract classes. Abstract classes are classes that cannot be directly referenced. So in the real world, in this example, you can have something that's just a dog. Maybe it's a mutt, maybe you got it and you don't really know what its background is, so it's just a dog. And so you can initialize a new dog, and that is perfectly valid. Same thing with Corgi and Pitbull, right? Because a Pitbull is a specific type of dog, you can totally just say, oh, you make a new Pitbull. But what is an animal? What is an animal that isn't anything else? There's no such thing, right? Animal is more of a concept than a concrete thing. And so because of that, animal, you cannot instantiate animal. It is an abstract class. And so perhaps animal is extended by dog, it can be extended by cat, it can be extended by lots of concrete classes, but animal itself cannot be instantiated. And abstract classes are useful because they kind of create this strict, this is the type of thing you are, but I won't tell you how to do it situation. A real life example of this is a list. So we have looked at linked lists already in this class before. And so in the real world implementation, list is an abstract class because list tells you all of the features that a list should have, but it doesn't tell you how you should implement it. And in real Java, list can both be extended by linked lists and array lists, which both offer concrete ways of implementing the list class. Similarly to abstract classes, we have interfaces. If abstract classes describe a class of classes, interfaces rather describe a specific action or attribute that a class can take. So the first major difference is that one class can implement multiple interfaces where they can only extend one class. So in this case, corgi is extending squishable and photogenic. Interfaces describe a narrow ability that can apply to many classes, but that may or may not be related to each other. A couple real-life examples are comparable, which says, can you compare this? And it forces you to implement the .compare function. And then also iterable, which we'll talk a lot more about next week, which tells you, oh, you can iterate through this. So these are specific actions that any class can take. A list can be comparable, an array list can be comparable, a hash map can be comparable. Like, they don't have to be related to each other. A cat may be photogenic, right? It's not specific to any type of class. Now let's quickly go over the implementation of all these things we just learned. So to define an abstract class, you write abstract keyword at the beginning of the class definition. For interfaces, instead of having the word class, you just have the word interface. If you want to extend a class, whether it's a concrete class or an abstract class, all you do is dog extends, and then whatever class you want to extend. And the last one is for implementing interfaces. You write the word implements, and then you write your interfaces separated by a comma. Now, the most interesting thing about all this subclassing and interfaces and all that are what happens to your functions when you do it. So the first thing we're going to talk about is method overloading. So these two terms get confused a lot, and it's important to know what they mean because they're both used often in this class. Method overloading is done when there are multiple methods with the same name and return type, but different parameters. So if one, let's say this is a dog class, perhaps it has a different reaction to barking at a dog versus another animal, right? So if you were to call bark at on a dog, then you would get woof, it's another dog. But if you were to call bark at on an animal, instead you would return woof, what's this? And so the goal of your system is to find the function signature that most closely matches what you're passing in. And so it will be able to tell the difference based off of the variable that you pass in. Method overriding, which is the second thing on this slide, is a little bit different. It sounds similar, but it's very different. Method overriding is done when a superclass has a method. In this case, let's say dog has the method speak that takes in nothing and returns void. And the corgi class also has a speak that takes in nothing and returns void. And so we are overriding our superclass's method by having our own. And so when your code runs, it'll go and look in your subclass to see if it has the method. And if it does, it'll just use that. If it doesn't, then it goes up to your superclass or your parent class and checks whether or not the method exists there. So overriding basically says, oh, I don't like the way my parent class handles this, so I'm going to do it a different way within myself. The very last thing we're going to talk about today is casting. So casting, which we'll talk more about actually Wednesday. So this worksheet does not go over casting a lot, but there is a line in the third problem on it, so I'm just going over it very quickly. Casting allows our compiler to overlook cases where we're calling a method that belongs to a subclass on a variable that is statically typed to be the superclass. As we've talked about before, the static type of a variable is the type that is declared on the left side when you create the variable. The dynamic type of a variable is what you actually put in it. So you can think of it this way. You can think of a variable being a box, A, and the static type is what it says on the box. It says this box can hold an animal. The dog, which is the dynamic type, is what we're actually putting in. So this box can hold any animal. So it can hold an animal, it could hold a dog because it's a type of animal, it could hold a corgi because it's a type of animal. It can't hold like a list because that's a completely different thing. So the static type is what's on the box, the dynamic type is what goes in the box. However, this creates a problem, right? So let's say the dog class has a method that says bark, and obviously the animal class doesn't necessarily have that. So if we want to call a.bark, this would actually error at compile time, because at compile time, our computer only has access to the static types. It doesn't really know what goes in the box yet, because to do that, it has to run through the code. So the only knowledge it knows is what the box holds. And since animal doesn't have a bark function, it would error. Now what casting allows us to do, if we did dog a dot bark, what casting allows us to do is tell the compiler, I promise, even though the box says animal, what will actually be in the box is going to be a dog. So first, obviously, the compiler checks to make sure would a dog even fit in this box, and the answer is yes. So it says, okay, I'll trust you, but if there isn't a dog in this variable at runtime, it'll error then. And so, if in this case our variable a holds a dog, and so this will run at runtime now. However, if animal A instead had a new animal in it, this would error at runtime, and this would error at compile time. Don't worry if this is a little confusing right now. We're going to cover it more in depth after all the discussions for this week are going to be over. Okay, just to review. At compile time, your computer checks for valid variable assignment. So it makes sure the thing in the box matches the thing you're trying to put in the box. And you might say, wait, you just told me it doesn't know what the dynamic types of anything is. Yeah, it checks the static type of whatever's on the left-hand side and the static type of whatever's on the right-hand side and make sure they match. After it does that, it checks that only valid method calls are happening. And so in this case, it would be making sure that this, for instance, where that our animal had a bark function. At runtime, it checks for overridden methods. So because it only has access to the static type at compile time, it's checking for the method calls in the static class, not in the dynamic class. So at runtime, it checks to see whether there is a better function in the subclass that is actually in the box. And then, lastly, it ensures that casted objects have been casted appropriately and that the things that it overlooked during compile time are actually legal. Okay, let's go over the worksheet now. The first question is about JUnit testing, which I hope you've all had a lot more practice in from the first part of the project. So before we get into what's on the screen right now, let's talk about the advantages and disadvantages of writing JUnit tests. I'll give you a couple seconds to think about what those might be, and then we'll go over it together. Okay, so what are the advantages and disadvantages of writing JUnit tests? Well, the advantages, there's a lot of them. A couple of them are that it keeps your code organized. Instead of testing your entire code at one time, JUnit testing allows you to test each module or component of your code individually to make sure that each of your building blocks is working. Because it's a lot harder to find a problem if you're checking the entirety of your code at one time, because if something goes wrong, you might be stuck thinking, I don't know which function is actually incorrect. The next part that's good is that it's useful in debugging your code locally and figuring out which part of your program isn't working. It's easy to step through on your computer. You don't have to deal with staring at your code and trying to figure out what's wrong. And it also reduces the amount of test code you actually need to write, because you can just reuse code across different JUnit tests. You can create helper functions, and that way you can test various actions or various edge cases a lot quicker. Great, those are a lot of advantages. What are the disadvantages? Well, there's only one real major disadvantage, and that is that it is hard to use for higher level testing. So JUnit tests are great for testing the individual components that go into writing a program, but they're not as useful for testing the entire program from start to finish. And so for that, we use other methods, which we'll go over later. But for now, all you have to know is how to use JUnit tests. So going back to the problem on the page. Think about the lab you did last week or the week before about JUnit testing. Fill in the following tests so that they test the constructor and the d-square list functions of intlist. I'll give you a couple seconds to think about it. Okay, welcome back. So let's first start off with the first function. So what are we testing here? We're testing the constructor of our intlist class. So the first thing we're doing is we're creating this intlist that's going to look like 3, 2, 1. Great. And so what we want to test now is we want to compare this against another verified way to create your intlist, right? And so an example here would be doing that. Because let's say we verified that intlist.list already works. And so now we can compare the results of our constructor to the results of using our list function here. So how we would do that is do 3, 2, 1, and x. And it'll assert equals if both of those are working. It'll assert equals will be true if both of those return the same value, and it'll be false if they don't. Now, here we have something that is very important to JUnit testing, is including this @ test. It's such a small thing that's so easy to miss, but your test will not run in that fancy way where you just click a button on the side and it shows you all of your correct tests and incorrect tests unless you have this here. So it's an important thing to not forget. So here the question is, what are we comparing, right? So we created our new intlist and then we destructively squared that list, right? And so now what do we do? Now what do we compare? Obviously, one of them is going to be the goal intlist. So we can make that intlist.list 149. And so what are we comparing it against? Well, since it's a destructive square list function, we can just compare it against L itself. Don't worry if you didn't get this as easily. This was more of just a practice in understanding how JUnit tests work. We will never test you guys, in this way. This is just more of a general conceptual understanding problem. Okay, moving on. Let's go to problem 2. we are given the animal class, as you can see here, and we want to fill in the definition of the cat class so that when greet is called, it says cat name says meow, rather than animal name says huh. So this is a problem that practices overriding methods. So I'll give you a couple seconds to think about it, and then we will come together. Okay, so the first thing that we have to do when we're starting this problem is create a constructor for our cat class, right? Because we don't want the noise here, that's here right now, to be huh. We want it to be meow. So what we can do is go and create public cat, which is just how we initialize a constructor, string name, same as the animal constructor. We don't need any more details. And then we have to call our superclasses constructor right there. This is required and it has to happen first. It can't happen later. So we do that. And then we can replace the noise that was set in the superclass with meow. So now the constructor is done, we can get to overriding our greet method. Oops. So we should use the tag at override. And it's not strictly necessary. The at override tag just tells your computer, oh, in this function, I am overriding a function from my superclass. And so the computer will yell at you if your functions don't properly match up. And this will prevent a lot of pain later on if you accidentally mistype the name or you accidentally set the parameter to be slightly different. The goal of this is an optional tag, but it's good practice. So we're going to do it. And then we do public void, because it has to match the greet function here. Public void greet. And then what are we printing? We're printing out something very similar to what we were printing out before, except we will be printing out system out print line. I do wish that this was shorter sometimes. Cat plus their name plus the word says plus make noise, which will now return meow because we've changed the value of that variable. And that's it. That's our cat class. That's the only thing we have to change because everything else will be handled by our animal class. Okay, great. Moving on from here, let's go on to problem 3. So now we're going to assume that animal and cat are defined as we did them in problem 2. And the question is now, as we go through this main function right here, what would get printed on each of these lines that has letter next to it? I'll give you a couple of seconds to think about it. Okay, so the best way to solve these problems, if you're given them on a test or something, is always to make an environment diagram. Doing so will help you keep track of anything that changes or any variables. It's just a good idea all around. So let's see, we have 3 things, right? We have an animal, A. So we can say that A points to an animal with the name Pluto and an age 10. We have a cat, C, which points to, I try to draw the box after, a cat with the name Garfield and an age 6. And then we have D, which is a dog with the name Fido that is an age 4. Great, so we have everything listed out. So first thing that's called is a.greet. So a.greet refers to animal.greet. So the first thing that we'll do is go back to our animal class and see what the greet function returns. And in this case, it returns this, which means that we can do animal, and the name of the animal is Pluto. Pluto says, huh? And that is, actually I don't think there's quotes in this. Says, huh? And that is what that first line prints out. So going on to the next line, we do something similar. This is c.greet, and this will be a cat named Garfield. Says, meow. And then lastly, we have C, which is our dog, and d.greet calls this greet function, which does dog, and then Fido says, and the noise that we've given it is woof, and Fido is less than 4, and if you remember from our function in the previous problem, animals that have an age younger than 5 actually return an all caps version of their noise, so it'll be woof, all caps. Great, so now let's get on to something that's a little more interesting. So here we're going to assign C to A. So now, instead of A pointing at an animal, it's going to be pointing at the class. And this is allowed because cat is a subclass of animal. So let's see what D is going to print. So here we're casting A to be a cat, and then calling .greet. And so by casting, we're saying pretend like the static type of A is actually a cat and not an animal, and that's what our computer does. So it checks to make sure that there is, in fact, a greet function in cat, which, surprise, surprise, there is. And so when we go to actually do it, we do cat Garfield again says meow. That's pretty straightforward. Now what's going on in E? So in E, we're not casting A. So let's go through what happens with the computer at compile time and then runtime. At compile time, we see that our computer checks whether or not A has a greet function. And the answer is it does. Great, so we're going to pretend like this is a function we're going to use for now. At runtime, we find out that what's in the box is a cat, not an animal. And so our computer checks to see whether or not there's any function in cat that directly overrides the greet function in animal, and in this case there is. If the function signature was even a little bit different, we would just be using the greet function in animal. But since it's not, we're going to use the greet function in cat. And so again, we're going to write the same thing. Cat Garfield says meow. Hopefully that wasn't too bad. Let's go on to some more hypotheticals. So the first thing is, consider what would happen if we added the following to the bottom of the main function under line 27. That's line 27 on the worksheet, is not line 27 on my slides. So we're adding these two lines. We're adding A equals new animal Fluffy and C equals A. So this will just create a new animal. That's a pretty straightforward thing. But C is a cat variable and A is an animal, right? So we have a box that's C and it holds cats or types of cats. And A is an animal, which is not necessarily a cat. So if we try putting A into the box, we're going to have error at compile time. And this is because at compile time, we check the static type of A, which happens to be an animal, and the static type of C, which happens to be a cat, and we decide that they don't match up. So we're not going to allow C to go into A. I'm sorry, A to go into C. If we were to replace this line with C equals cat A, we would pass that initial check. The computer would trust us and say, okay, I'll believe you that there is a cat in that variable, that there's a cat in that box, and so I will proceed as if this checks out. And then at runtime, when we try to put an animal into the cat box, it'll error then instead. Figuring out when things error can be a little bit tricky, so don't worry if this seems a little strange to you right now. You will have plenty of practice in the coming weeks. Now let's consider a second hypothetical. So let's say we add these two lines to the bottom. A equals new dog and D equals A. So again, at compile time, all our computer sees is that you have a box that fits a dog called D. And in this box, you are trying to put A, which is, as far as the computer knows at this time, an animal. So this will cause a compiler error. Now, what if we were to do instead D equals dog A? Well, in that case, again, like I mentioned in the previous problem, our computer will pretend like A is statically typed as dog and says, okay, I'll trust you that there will be a dog in this when we come across this line in runtime. And then at runtime, since A actually does hold a dog, we'll just be putting a dog in a dog box, which is perfectly fine. So this won't error at all. It'll be perfectly acceptable. So this is an example of where using casting is useful. I'm sure you've already used it in your linked list, or not linked list, array deck implementation, because for instance, you could not create an array that is typed T. You would have to create an object array and cast it to pretend like it's a T array. This is a very similar concept. Okay, so we've gone through most of the worksheet, and the next problem is one of the hardest problems on a discussion worksheet in this class in general. So let's try going through it. I couldn't fit all of it on my slides, so please have your worksheet pulled up, and I will give you a couple seconds to look at it. The goal of this is to cross out any lines that cause compile time errors or cascading errors, which are just errors that occur because an error happened earlier in the program that's related to this, and put an X through any runtime errors. I'll give you a bit to think about it. Okay, welcome back. So first, let's just go through class A, B, and C and see if there's any errors that we can find there. Looking through class A, this line checks out, this line checks out, this line checks out, this line checks out. Same with all the lines in B. Oops. This is fine. This is actually perfectly allowed, if you were wondering. This is also fine. Here we hit a bit of a problem. You can't actually do super dot super. It's not a valid thing. You can't access another class's super through a variable. It's just not allowed. It's like calling this. Only the class you're currently in is actually allowed to call super. So this would actually error. So we can just pretend like this is commented out for the rest of this problem. And the last line also checks out. So looking at class D, there's a lot going on, which I will admit. So the first line says B BAO equals new A. So this immediately errors. And I want you to think about why this might be the case. This immediately errors because class B extends A. So all B's are A's, but not necessarily the other way around. It's similar to our shoving an animal into a dog box analogy from the previous problem. It's not allowed, so this line's going to error at compile time, because it can check the static type of B and the static type of A and say, that doesn't look like it's going to work. The next two lines are cascading errors because A0 doesn't exist because it errors out. So A0M1 and A0M2 both also don't exist. Now we get to A B0 equals new B. And this line is perfectly fine because all B's are A's, so you can put any B into an A box. Next we go to system.out.print B0.x. And so this prints out whatever is stored in B0.x. We go to B0. We go to B0, which contains, we go to B, which is a dynamic type of B0, and it does not contain a variable x. So instead we go up to its superclass and we notice that there's an x right here, so that's what we're going to return. So that's going to return 5. Moving on, we go to B0.M1 and B0.M2. B0.M1 reference for B0.M1 at compile time, we check the static type of B0, which again is A, to make sure that there is an M1 function, and there is, so it doesn't error. At runtime, we go back and we say, is there a function in B that overrides M1? And the answer is no. So we print out AM1, 5. Next, for B0M2, we do the same thing. At compile time, we check whether A has a function that's called M2, and in fact does, so we let that slide. And then at runtime, we go back and check, is there a function in B that has the same function signature and therefore overrides the function in A? And the answer again is yes. So this one actually prints BM2, 5. Going on to the next line, we have B0.M261. And so we do the same thing we've been doing up until now. We go back to A because it's a static type of B0, and we check to see whether or not there is an M1 or an M2 that takes in an integer as a parameter in the class A, and there isn't. So it errors at compile time. Even though there is something that takes in an integer in B, because B0 is statically typed as A, it doesn't matter. We never get to the point where we can check B in the first place. So that happens, and now we move on to B. Let me erase this. B1 equals new b. And this is perfectly fine. The static and dynamic type are the same. Nothing to even think about here. So now we can do b1.m261. And this is perfectly valid because b is the static type. So we go there and we find this function immediately. And then at runtime, the dynamic type is also b, so we can just print directly. So this prints out bm2y61. Now we can move on to the next function, b1.m3. And so again, we just check b, there is an m3, we're all good, so it can return bm3 called. Great. Okay, so moving on, we're going to now define another variable. This one is ACO equals new C. Even though C extends B, because B extends A, C is considered a subclass of A, even though the relationship is not direct. So this is also perfectly fine. We see CO dot M2, and this is perfectly valid because we go to A and there's an M2 right here. And then at runtime, we check whether the dynamic type, which is C, has a function that perfectly overrides the function we found in A, which it does. So we return whatever this function puts out, which is cm2 super.x, which is just 5. So next, we go and we create another variable called C1 that is of type C. And we try to put in a C, but we cast it to be an A. And again, going back to the animal and the dog box analogy, even though this variable is a C ultimately, because we're statically typing it to be an A, it doesn't work. And it's going to error at compile time. Now we have A1 equals A C0, and this is fine because C0 is of type A already. We didn't really have to even cast it, but it works even if we do. Now we have C2 equals CA1. Maybe look like a 1. So A1, if you would recall, is over here. And so since A1 contains a C ultimately, this casting works. And so A1 is actually this C object that we initialized up here, masquerading as an animal. So by casting it as a C, we're telling it, don't worry, it's been in a lot of animal boxes, but ultimately there is a C in here. And so this checks out perfectly fine. Now let's go to C2.M3, which, let's see, at compile time, we go to the static type of C2, which is the class C, and we find this function. We don't find a function in C, but of course we then have to check its superclass to see if there's a function there. We check and we see M3 right here, and so it checks out, and at runtime we run that same function, which gives us bm3 called. Next, we try running C2.M4. At compile time, we notice that, if you'd recall from earlier, we actually commented this out because it's an invalid function. So there is no M4 in C. We go up a level, we check B, there is no M4 in B. We go up another level, we check A, there's no M4 in A, so there's no M4 at all. So this is also going to error. Next we go to C2.M5, and this one checks out because again we go to C2, we see that there is an M5 that is available to us, passes the compile check. At runtime, we just go and evaluate that function, which gives us CM5y, and y equals x plus 1, so it's 6. We're almost through, guys. So now we have C0, which is casted to be a C, dot M3. And so we're going to cast C0 to be a C. So we're going to first check whether there's an M3. First, we have to check whether C0 can be casted as a C. So if you look where C0 is defined over here, C is a subclass of A, so that checks out where we can try casting C0 as a C. And then we check the C class to see if there is an M3 there. There isn't one in class C, but there is one in class B, which it extends, so that's fine. It passes the compile check. We go and we return at runtime, and we evaluate the function that we decided on earlier. So we get BM3 called. Okay, I'm running out of room. So the next function that we're going to do is COM2. And this looks an awful lot like we just did, except the casting is not attached to the variable with parentheses. And so what this is actually doing is casting the result of this call. And so because of that, we check to see if the static type of C0, which is A, contains M2, which it does over here. And so then at runtime, we check whether the dynamic type of C0 overrides it. It does down here. And then but the problem is that this returns void, right? So this returns nothing. You can't cast nothing to be a C. And so this actually will fail at compile time, because at compile time, your computer makes sure that the things you're casting are allowed to be cast. You can't cast null to be some object because your computer knows that null could never actually be a C. So this is actually going to error at compile time. And then we go to b0.update. We call that, and b0 is statically typed as A. We check whether A has an update function. It does. And then we go into our dynamic type, B. We check whether B has a different update function. It does not. And so this just updates our x to be equal to 99 for only B0. X is not a static variable, so this only affects B0. And then lastly, B0.M1, which prints out, which static type checks to see that there's M1 here. There's no M1 in the dynamic type, which is B. So we're going to evaluate this function, and it prints out AM1 99. And with that, you are finally done with this problem. I know there's a lot going on, and it's a little confusing, but it's really good practice for dynamic method selection. So I'm happy you stuck around. Anyway, I wish you guys all luck with the rest of your week and with the first midterm in this class. I'm sure you're all going to do great, so good luck and see you next week.